Well, welcome back for the last in this series of talks. Our last speaker is Cumrun Vafa. Cumrun got his PhD at Princeton under the direction of Edward Witten. He then went to Harvard as a junior fellow, and he is still at Harvard as the Dunner Professor of Sciences. One of many honors recognizing his achievements is the 2008 Dirac Medal in theoretical physics. Cumrun is a leading string theorist whose work has received over 30,000 citations. A physicist must cite more than the mathematicians, Cumrun. One of his most famous works was his co-discovery with Andy Strominger that the Hawking entropy of a black hole can be computed by counting the quantum states of a system of d-branes, which models the black hole. Another is the development of F-theory, which unites many of the previous string theory constructions and suggests new approaches to making real-world predictions from string theory. He has made numerous contributions to string duality, topological string theory, and many other topics. Cumrun, his title is Wall Crossings Old and New.
Thank you. Well, thank you very much for the introduction, John, and thanks for inviting me to give a talk here. It's a great honor and pleasure to be part of this inauguration event for Simon Center. I'm going to be talking about a number of works, really, which I've done over many years, actually in the span of more or less 2 decades, but there was a big gap in the middle of it, so to speak. So sometimes the beginning of 90s, it was a joint work with Ceccati, and in the past year, in two or three papers with Ceccati and Knightsky, where we developed it further. So there are many beautiful connections between physics and mathematics, and I was thinking of choosing one, and in this context, I thought about the wall crossing. And in many of these examples, supersymmetry plays a key role. And this is the case also for the example I'm going to be talking about. It has become one of the most interesting topics in the past couple of years, one of the hot topics, so to speak, in the math-physics joint area. And has been lots of developments going on in this direction. So I thought it might be suitable for a discussion here. And it was also precisely for this fact that there were at least 2 workshops related to this topic here already at the Simon Center. One was last spring, if I remember correctly, and the other one is the past summer. So we already have had 2 workshops on this topic here. And you might ask, what is wall crossing after all, even though it's a hot topic and a group of people who are working on it. It may not be well known, so perhaps this picture might help. But, well, this is the picture from our workshop, which emphasizes the topic. But actually, what is wall crossing? So consider a quantum field theory, which I call Q here. A quantum field theory will typically depend on a bunch of parameters. I'm denoting here by Ti, the moduli space of the quantum field theory, where things change and vary as we change these parameters. So for example, if you choose a particular point on this moduli space, you have particles with certain spectra and certain properties. Perhaps to visualize it better, I draw the particles. So let's say we have 3 particles. One of them is very massive, one of them is lighter, one of them is a medium mass. And we can change the moduli, and the masses change. 2 of them are becoming heavier, one of them is maybe becoming lighter. And we changed it, and then suddenly one of them disappears. And this phenomena might originally be a bit difficult to swallow. What happened? We were counting the particles. There were 3, and then suddenly became 2. It sounds like discontinuous. Something discontinuous happens. Well, across a wall in the parameter space where this happens, we're calling this wall the wall which we cross. As we change the parameters, the number of particles jumps. There's something discontinuous apparently happening Even though I should add that the parameters typically are smooth parameters, and we don't expect anything non-smooth in the correlation functions. So the whole data of quantum field theory is smooth. But nevertheless, something should happen as we cross this region, codimension 1 in real space of this moduli space when we cross it. And this is what we want to study. So the quantum field theory of interest is supersymmetric, as I already mentioned. And the two particular cases that I will focus on are quantum field theories in 2 dimensions and quantum field theory in 4 dimensions. Bulk of my talk will be related to the simpler case of 2 dimensions, and then I will outline how the 4-dimensional story fits into that 2-dimensional context. In the 2-dimensional context, the theory we are going to be studying, the n equal to 2 supersymmetric theory, is characterized by a holomorphic function. So you think, take a function W called the superpotential. It's a holomorphic function of a bunch of variables, xi, which we just think of parameterizing Cn. So nothing deep topology next. Basically, the only information, non-trivial information in terms of this holomorphic function. For example, you can imagine this some kind of a polynomial, let's say, or it could be other forms, but let's just, to focus on one example, think about some polynomials, polynomial expression in these x's, which are these parameterized Cn. The moduli of this quantum field theory in this context will depend on the parameters defining this W, the coefficients of this polynomial in particular. They will be holomorphic. So this space, M, is naturally a complex manifold, if you wish, parameterized by these complex coefficients of this superpotential. So let's be very concrete. This talk, I really want to be concrete as much as I can. So I try to give you a very concrete example here. Take the W depending only on one variable. So we have one field here. And we just have a cubic potential, cubic polynomial with the lower term, which is linear, I take. And the coefficient here, A, will be that moduli space I'm talking about, for example, where the theory depends on. The vacua of this theory are given by the critical points of this potential, because the actual physical potential is a square in absolute value of dW. So therefore, the minima of the potential correspond to critical points of W. And I will be assuming that we have isolated critical points. Just like this example, we will have 2 critical points given by plus or minus square root of A. So this is the X space, and here I'm denoting the 2 vacua. So near these, you can choose one of these 2 vacua to sit in if you want to be at absolutely lowest energy. And theory is supersymmetric, so the actual energy is actually exactly 0 at either of these 2 vacua. It's exactly degenerate, and we have 2 vacua. But now one thing we can do, since now recall we're talking about the theory in 2 dimensions. So we have one space and one time. So if we're talking about one space, we can have a configuration in the space where on the far left on the space, we are in one of the vacua, and the far right, we are in the other vacua. So we can have a configuration which interpolates from one to the other vacuum. These are what physicists call kinks, and they are just simply just suitable configurations which somehow map the real line to this some particular trajectory in this X space. So pictorially, if I denote the space by sigma, and this X is this complex direction, so you start at far left in one side of the space at one of the vacua minus square root of A, and as you change your parameters, as you go to the right-hand side, you change the X, so that becomes this plus square root of A. Of course, you can, in principle, consider a very complicated trajectory from minus A to minus square root of A to plus square root of A. But one thing which is kind of typically obvious from this is that there is going to be at least a minimum configuration that you might look for in this space. In terms of energy, you want to try and minimize it. So you look for a particle, therefore. So in this context, we say you have a situation where on the left and the right, you have basically 0 energy. But in the regions where the space, when the X is varying, you have some energy. And so this will give rise to a mass. So you can think about this as a particle whose mass is kind of a little spread out, not at the one point. And these are objects that we were trying to find, to focus on. To get the actual minimum energy configuration, it turns out we have to solve an equation of this form. It's kind of like a gradient flow captured by this W, or in this case, it's the holomorphic W, the complex conjugate of W. So we look at an equation dx d sigma, where sigma is the space, is equal to up to some phase, some fixed phase, dw bar dx. So it turns out that these configurations for suitable alphas, for suitable choice of phases, minimize the energy. And this is related to the fact that if you take this to the other side and you square it, it's related to the actual energy in the Hamiltonian. So therefore, you want to minimize it. Out of that square term, there's a cross term, which is the leftover piece, which gives you the mass of the corresponding particle. So the mass and all that is all fixed by supersymmetry once you have these configurations, which are called the BPS configurations. So if you look at so the map we had was from the real line interpolating between two vacua. So if you look at the map from x to the W plane, which is this W of x map, straightens it out, this line. So that's basically the fact about the W. So these BPS configurations are simple in the W plane. They're just straight lines. So it can kind of be seen from here if you just look at how dW changes with sigma. You get dW dx dx d sigma, so you get dW squared up to an overall phase. So it's a positive direction up to a given direction. So you just go straight in that direction, the W. So the phase of W doesn't change, it's in a given direction. So the BPS configuration is simply given by mapped directly to these straight lines, which go from one vacuum value to the other value. But that means, in particular, we have an easy time actually deciding what these trajectories are. Namely, we simply draw a straight line, and we take the preimage. And the preimage would, in principle, give us the kink. Sounds like a straightforward thing to do. In general, the masses, if you take a generic configuration in this particular sector, which you interpolate from the vacuum I to vacuum J, from left to right, the mass is bigger than or equal to the absolute value of the change of the W. In other words, in the W plane, the distance between the critical values is a lower bound of the mass. And the BPS configuration saturated. The configuration for which some supersymmetry is preserved, are precisely the ones which saturate this bound. So these are the ones we would like to discuss, but somehow I was talking about the particles, and somehow the number of particles jumped. In the example, I said it could jump in some way, but how could they jump in a smooth way? The idea is not that complicated. If you have a particle labeled by an IJ vacuum, it could decay to a particle IK from the IK sector, and then another particle from the KJ sector. In other words, the particles do not have to be stable. They can decay. So when I was talking about these are my particles, I should have been more precise. I should have said these are my stable particles. Of course, the unstable particles, they will decay away, so I'm not focusing on them. So the unstable particles, a stable particle can become unstable continuously as you change parameters, and that's what we should be looking for. So the jumping phenomenon simply refers to instability of what would be the BPS stable particles, that's all. And that could happen through these processes. In general, the particle, for it to decay, its mass should be bigger than the masses of the things it's decaying to, bigger than or equal to it. So Mij should be bigger than or equal to Mik plus Mjk. But that seems to be hard to do because the change in this is a simple identity, which we learn in, I don't know, primary school, high school, somewhere we learned this, that this can't be done for triangles unless we give up the triangle. And if you want Ij distance to be less than the sum of these are equal to it, the only possibility is equality, and that's if you actually align these critical value in the W plane. So in this case, an Ij particle can decay to an Ik plus a Kj particle. So that's at least the case where we can have. So in principle now, we can find the regions of marginal stability. Namely, these walls of marginal stability are precisely the cases where this is marginally stable. That is, the particle in the Ij sector just becomes barely unstable. And namely, the masses of Ij could be equal to mass of Ik and Kj, so it could potentially decay right after that. And the condition for that to happen is, as you can see, is a simple condition on W. You just ask which parameters you choose for the polynomial so that the critical values are aligned. Those are the regions that give you these walls. So let's consider an example again. Take a quartic, again, I have just one variable, and superpotential depending only on this in the quartic form, minus x. If you look at the critical point, there are 3 critical points. There are the roots of unity, the 3rd roots of unity. And you can see that if you just look at the critical values and so forth, if you look at the pre-images, you find the corresponding kinks. And you see that there is exactly one kink between each pair of vacua. So this is the case where we have 3 kinks, 3 particles, and that's the answer to this problem, just by simply drawing straight lines in W plane and taking the pre-image of them and finding the corresponding map. So now imagine changing the parameters of this W so that now 2 of these become aligned, 3 of them become aligned. So in this case, what happens, just as they are becoming aligned, you have one kink and the second kink, but the 3rd one is more or less retracing the first 2. So then you could say, okay, what if I pass through this configuration? So you had it aligned. Now we go through this configuration, which was alignment. You go to the next configuration. You say, how could you disappear? How could this particle disappear now after this? All you do is just take a straight line in the pre-image. But that's where we have to remember. This is not the one-to-one configuration backwards, right? So there's a problem. We cannot have a pre-image of a critical value may not be a critical point. In other words, right after you pass through this configuration, if you take a straight line here, that straight line, the pre-image of it will end up at a point which is not a critical point of W. So not every straight line in the W plane will translate to a kink. Some of them don't, and you have to check which ones do. And precisely as you pass through these aligned configurations, one of them which used to be okay becomes not okay, becomes a bad point. In other words, the critical points will, the point that will be pre-image of the critical value is not the critical point of W, and therefore this putative kink is actually not a kink. Therefore, we'll have disappeared one of the kinks. We started with 3 kinks here. And if you, for example, go from this polynomial to this one, you can check that here you only have 2 kinks. It's actually easy to see in this case why you have 2 kinks. If you look at the critical points, you find the critical points are not too hard to find, 0, 1, minus 1. And the critical values of the 1 and the minus 1 are equal, so therefore there cannot be a mass between them because it would have been 0 mass, and that's not the case. So therefore, it's clear that you will not have 3, and in this case, you only have 2. So this is a very simple situation. We just described how the kinks disappear, no magic, simple. In something simple algebra, you can almost give it to a good high school student who has learned about complex geometry. Now you can extend it to higher dimensions. After we have graduated from the dimension 1 complex, we can go to n-dimensional complex situation. So we have W of x. Again, you look at critical points. We assume they are isolated. Again, you look at the kinks, which now in this case will be, again, a flow equation like this with some fixed phase. And this fixed phase, again, should be the phase aligned in the direction in the W plane, which the particle, which is the kink you are trying to locate. So here this becomes a bit more tangled up. My pictorial skills also become a little bit more limited. But here you have to recall that W is one-dimensional still. It's a complex plane. But you have a map from Cn to C, which is this map from the X space to the C to this plane. So you look at the pre-image, but you cannot just take the pre-image of the line and find the pre-image because that would be a wrong, even not the corresponding equation that you're solving. It's not going to be a line in that case in general. So what you do is, if you go and try to solve this equation near the critical point, what you find is that you get a whole host of possible solutions emanating from a given critical point, which is, so in other words, if you follow the solution near this particular W and you follow a little bit to the right, let's say, towards the other critical point, you find that there's a potential of all a sphere worth, or generally a sphere worth of possible solutions, which are what is known as the vanishing cycles of this singularity. So this could be viewed as the cycle which vanishes at this point. This is a critical point of W, and that's the corresponding cycles which vanish at that point. So these would be putative solutions for the kink. You can do the opposite from this end, going the other way, and you find a putative cycle, which is a collection of solutions which correspond to the cycle which vanishes on the other end. So any point on this blue sphere or green sphere could be a putative solution, but for the solution to make it, the solution should go from here to here. And for that to happen, points should coincide. Therefore, for each intersection point of these two cycles, you get a solution. So the number of kinks going from the ith to the jth is simply the intersection of the corresponding vanishing cycles along this trajectory. So there's simple geometry associated with them, and so we can simply reformulate the number of kinks in terms of this intersection. There's some sign involved, so the intersection, one has to be taken care of with respect to that. So there's sometimes you cancel that to get the net number. So these are the net number of kinks. And in fact, in this context, we can use the Picard-Lefschetz theory, old classical math work, which tells us how the number of kinks are going to change. So suppose we have a situation like this, where we have critical values given by I, j, and k in the w plane. And let's say one of the critical values is going to cross the line between the other two critical values. So you take a point in the middle there, and you choose a basis for the vanishing cycles, which correspond to cycles which vanish at each of these three different points. So let me call the vanishing cycle at this point delta I, the other one delta j, and the last one delta k. The number of kinks from I to j is just the inner product or intersection of these two cycles, delta I, delta j. And similarly for the number of kinks between j and k is delta j, delta k. And the number of kinks from I to k is delta I, delta k.
Are you always assuming that w is a polynomial function of the variables?
Here I'm assuming for this discussion, but in general we don't have to. This generalizes. In fact, this could have a non-trivial topology and all that, but for the purpose of this talk, you could assume it's just polynomial. So what are we going to do? We're going to now move this over here. So you see one of these cycles is not going to be in the right place, this guy. So we have to move it around the other side to get the right number of, to get the right cycle after this point has moved over there. So once you do that, the number of kinks that you're going to get now has shifted. You see that the Nij doesn't change, but Nj, see what happens? So the k prime changed according to this formula. So the formula is delta k prime is delta k minus delta j times delta k times delta j. This is the monodromy of Picard-Lefschetz, which tells you how the cycle changes according to the intersection with the other cycle. And if you plug it over here, you find that the only kink that changes is the kink between I and k. The number of solitons going from the vacuum I to vacuum k changes simply by the product formula, namely n prime ik is nik minus the product of the number of kinks you had from ij to that of jk. There's an orientation in the story, which if you go one way or the other, this sign could be plus or minus, so you have to keep track of orientation. This can also be formulated in a following language, which might at first sound a little strange, why we're doing this. So let's consider V to be the space of vacuum. And for each, consider the operators Tij for each kink configuration, which goes from the ith vacuum to the jth vacuum, which is simply the identity operator in this space, plus the number of kinks from I to j times the ij vector. In other words, you have, in the matrix notation, you have these upper triangular kind of operators, which is diagonal 1, and the upper entry is the ijth element of this operator. You just put an integer, which is the number of kinks from the I to the jth vacuum. And Eij, you can think of it as the operator which takes the ith vacuum to the jth vacuum. So this process of moving this j through this ik line from this point, from here to here, in other words, can be also phrased in terms of what happens to the w's. So let's consider this is the corresponding difference in the w's, wij, wjk, and wik. So let me draw them here. So these are the difference of the W's, and remember that the masses were related to the difference of the W's. So what happens as we go around here, these two lines come and get aligned to WIK, and then they move over. So they kind of go around. One goes one way, the other one comes the other way, and they switch orders. They switch their places. For each of these kinks, we already defined, for each of the I and j, we have already defined an operator. And what we're going to do is the following. We're going to introduce an operator, product of these. You take this operator from this space V to itself, but now it's a composite operator, which is a product of three of them, ordered according to the phase of the corresponding W. Namely, each one of these particles is associated with a given phase in the W plane. And you order these operators according to that phase, and you multiply them in that order. So you get Tij, Tik, and Tjk. And the main information in these T's are basically the number of the kinks in each sector. After you have switched their orders, you also use the new T's because the T's have changed, because the number of kinks have changed. So you put the new T's, but you order them differently because now the orders of Jk and Ij have switched over. So you get this product. And the statement of this Picard-Lefschetz monodromy simply translates to the statement that this product is invariant. This product did not change. Yes?
Is this some sort of Yang-Bax equation which mentioned in the first lecture?
There might be a relation, but in this form, this is far more too elementary compared to the talk we heard this afternoon was far more advanced application if it was Yang-Bax. This is a very trivial statement. It's a linear algebra here. Yeah, it looks the same. Yeah, maybe there's deep relation, but my aim here is not to explore that, but maybe. But now there's something natural we can do. We can take all the particles in the theory, all the BPS ones, not just the three of them, the ones that are getting aligned, and look at all the possible W's that we're getting in the W plane. They're given by this complex plane, so you order them according to whatever phase they have, and you go around this order of these W's, and as you go around each one of them, you pick out the corresponding operator which corresponds to that particular kink. You take the product of all these operators in the order of the phase you get, and then you get an operator M. But now the eigenvalues of M are well defined. In other words, now we have gone full around and we have come back to itself. Of course, depending on where we start, we will get a different M, but it's related to it up to conjugation. So in other words, the eigenvalues of M are invariants of this data. And we said that if you change the parameters of W, the eigenvalues don't change because this monodromy structure doesn't change. That was the invariance. Therefore, what we are saying is that you give me a polynomial, I'll give you some eigenvalues. So if you have a polynomial, let's say, which has n critical points, I'm going to give you n eigenvalues out of nowhere. So somehow associate to the polynomial, which does not depend on the coefficients of the polynomial, just the invariant data of the polynomial. So you give me a degree n polynomial, pops out n eigenvalues from just this computation. So the question is, what is the relation of these eigenvalues with the corresponding polynomial? Let's assume that W is a deformation of a quasi-homogeneous function. So we start with, we think about W as some quasi-homogeneous W plus lower order, lower weight deformations of it. So W naught is a quasi-homogeneous in the sense that if you rescale xi by some weights, lambda to the qi, these q's are the weights of x's, then the W gets rescaled by lambda. You can get rid of the lambda. And these, so in other words, the whole W naught can be said to have weight 1 under lambda. These other delta W, we think of what we call relevant deformations, which are lower order, lower weight than 1. So made of monomials of some kind, which have weight less than 1, this condition. So let's assume this configuration. So let's see what we get in this case. Well, again, let's go back instead of giving you the full theory. Let me start with the example. X cubed minus epsilon x, our favorite simple example. We have 2 points. There's one kink. And now we want to compute our M. M is going around the whole plane. We have a kink at one particular value, an anti-kink, the opposite kink from the opposite direction with the opposite value of W. So the phases are oppositely oriented. So as you go around the first one, you get the kink which is given by the identity and the 1 here, denoting that there's a 1 kink going from one critical point to the other. In the other point, you get the kink with the one in the opposite order. There's actually a sign you have to be careful about, which which can be defined carefully, but there turns out to be a minus sign here instead of +1. So the full monodromy is basically the product of these guys. This always turns out to be related to this guy by inverse transposition as a general rule. So if I did it correctly, but anyhow. So you take the product of these guys, you get some matrix like this. And if you take this monodromy and you find these eigenvalues, you find that there are 6 roots of unity, the 2 6 roots of unity, the primitive 6 roots of unity. Now you look back at this W, and W is x cubed. So you say, let me forget about this lower term. Let me just look at x cubed. And you say, well, there's a natural ring associated with this singularity, which is, in the physics context, is the chiral ring of the supersymmetric theory, given by the monomials, the ring generated by x, modulo the ideal given by dw. So the ring has 2 elements, 1 and x. And if you now use the fact that this x cubed has a gradation, you can, if you assign grade 1 to w, x has grade 1/3. So these will get here the weight 0 and the weight 1/3. So in other words, if omega is a 6 root of unity, you get 1 and omega squared as the corresponding weights of these 2 monomials. And you find that these are exactly the 2 eigenvalues you had, up to an overall multiplication by omega, which kind of symmetrizes the 2 values here, 1 and omega squared. Now, the fact this example I just told you turns out to be a generally true statement. That is, if you did take the quasi-homogeneous singularity, deform it, compute the intersection of these vanishing cycles, compute this full monodromy matrix, compute its eigenvalues, what you find is given exactly by the same eigenvalues, the gradation of the ring, the singularity ring, up to an overall multiplication by 1 factor, which is basically symmetrizes the eigenvalues. So in fact, we can take a power of this monodromy. If you take the trace of this monodromy to some power, m to the k, you can think about, at the quasi-homogeneous case, when you actually ignore this term, just look at the analog of the quasi-homogeneous W, you have a symmetry in the theory, which is this rotation, phase rotation of the corresponding fields. And you can basically show the following fact, which is very non-trivial, that the trace of this monodromy matrix to the kth power is simply the trace of this gradation, or this what we call the R charge, to the power of, or R symmetry operated to the power of k. Now, the ring that I was talking about gets related to the vacuum of the Hilbert space, and this also includes that shift that I was telling you about in the phase, because you're going from the Nouveau short sector of the theory to the Ramon sector, and basically studying a Witten index for that ground state, except that you have twisted the Witten index by this operator G or some power of it, and that's what we're computing. So on the right-hand side, we know what we're computing. We're computing a Witten index, except twisted by some symmetry of the theory, G, or some power of it. But the left-hand side does not look like an index of an operator naively, because there's no symmetry anymore. As soon as, in order to have kinks, you have to have gone away from quasi-homogeneous limit. So there is no such G anymore. G only makes sense when you have a quasi-homogeneous polynomial. When you went away, the G doesn't exist, but now that's where you get the kinks. Then you count the kinks between the critical points, and you compute this trace of this monodromy, and you get a relation between the weights of this quasi-homogeneous the polynomial and the ring that generates it, and the corresponding trace of this operator. So for example, if you get, there's a closed formula you can in fact write down. If you want to compute trace of m to the k, which is in the quasi-homogeneous limit, it's this object you would be computing, turns out to be simply related to the product of 1 minus these weights divided by the weights of each of these monomials, restricted to the weights such that k times q are integer. Now, this formula can be proven, and I'm going to give you a brief idea of how to actually go about proving this, but But before I do this, why is this interesting? Why are we even talking about this kind of question? Well, if you rescale W by some amount rho, the masses, which is the difference, the masses of these BPS particles are given by the difference of the critical values, and therefore they will be rescaled by rho. So if rho is large, you're making the masses large. If rho is small, you're making the masses small. The limit at which rho goes to 0 is the limit where you can actually get rid of, by a change of variables, you can get rid of this non-quasi-homogeneous part, which is a lower weight. You can get rid of that weight. So as rho goes to 0, W approaches, by change of variables, to the quasi-homogeneous one, W naught. That's what we call the ultraviolet limit. That's the case where the masses all go to 0. In the other limit, where rho goes to infinity, you have a very massive theory. That's where everything is becoming massive. This is the infrared limit of the theory. Now, the index we were talking about made sense in the ultraviolet limit of the theory. So we're computing some index at the ultraviolet theory. That's the case where the theory becomes conformal. And then we deform it to a massive theory. And somehow, embedded in this massive deformed theory were the imprints of this conformal theory somehow, because we were able to recover the information about these spectrum of these R charges simply by counting these kinks. So, but how do we prove this statement? I just stated to you the result. I didn't tell you how to prove it. Now I'll give you the idea of the proof. The idea of the proof is to define an index which makes sense for arbitrary rho and interpolates between the rho equal to 0 and rho goes to infinity limit, and basically trying to generalize this away from the naive limit that we studied. But it turns out that it suffices to focus on reducing the theory from 2 dimension to 1 dimension and discuss the simple supersymmetric quantum mechanics. However, what we end up doing turns out to be a novel version of a supersymmetric quantum mechanics in which the phase of W gets identified with time. So usually we don't. This is something we almost never do in physics, and if our students do it, we throw them out. We say don't introduce time-dependent things directly by hand into the Lagrangian. Here I'm doing exactly that. I'm taking time-dependent explicitly, breaking what the sacred principle of symmetries, the Lorentz symmetry, etc., is in the corresponding theory. So we change our theory to something we usually don't do. We put time dependence in the phase of the potential. So now the phase of W is labeled by time. It correlates, it aligns with the time. So this sounds bizarre from the viewpoint of supersymmetry, because the whole point of supersymmetry is that the Hamiltonian is a score of supersymmetry operator. Q squared is H. So if you put a time dependence like this, the usual Hamiltonian is not the usual evolution you had. You wouldn't have that symmetry. Time translation is not a symmetry in this problem. And it turns out, nevertheless, you can have a twisted version of quantum mechanics which preserves some supercharge. So we can define the corresponding supersymmetric theory. It's just not the standard one. So very similar to what Ed was describing in his talk, you get a localization to a particular configuration, which in this case turns out to be dx dt minus e to the it del w bar is 0. So this will be the analog of the localization of the type that Ed was talking about in his talk. Notice here that I have just talked about the reduction of this theory from 2 to 1 dimension, so I only have time left over. So you're just simply solving this kind of an equation. So let me rephrase this mathematically. So mathematically, we're computing a degree of a map from an infinite dimensional space to itself, some particular order, some particular map, and we're computing that degree. So what is that space? The space is the map from a circle, which is identified with the time, to complex n-dimensional space. So let's call this infinite dimensional space Y. And the map we're taking is a map from Y to Y given by H, where H is simply the derivative of x with respect to time minus this phase. And we're counting the degree of this map. One way to do it is to take the preimage of 0, where this vanishes, and count the number of preimages taking into account orientation. So that's what we basically want to do. So we're trying to find, therefore, solutions to this configuration, which is basically computing the preimages of this map. But the degree should not depend on changes of these parameters. Invariant, topological invariant, or in this case, supersymmetric invariant. You can change the parameters, and in this case, we can rescale W by a large amount. If you rescale the W by a large amount, you see that it's hard to solve this equation, and the obvious solution is to take x dot to be 0 and to be sitting at the critical points. So a natural set of solution will be just looking at the critical points of W, which we were talking about before, and just sit there for all time. So x dot and this are separately 0, and this is going to work. However, you also notice that this is exactly the kind of equation I was writing for the kink. Except that for the kink, this was a fixed phase, and this was dx d sigma that I was talking about, which now will enter our finding these other solutions. So we can use the operator formulation of quantum mechanics to compute the partition function. So now we switch gears. So you have this path integral for the supersymmetric quantum mechanics. Now we form it in terms of the operators acting on a Hilbert space. The natural Hilbert space for a generic one is just the space of these vacua, the critical points. So on the time evolution operator I talk about with you, denoted by U. So if you have these vacua, as you evolve in time, nothing is happening, you're sitting in the vacuum, so you get an identity operator. Except, after we rescale W by a large amount, we see that there are some particular times in which this phase aligns with the phase of a BPS particle. And so what used to be a BPS kink here becomes what we could call BPS instanton, which at a particular time can interpolate from one vacuum to another. So you get new solutions. In other words, in addition to the old solutions that you had, you have now a possibility of going from one to the other at the particular time t naught. So this is going to be a new kind of configuration. So they both contribute to this path integral, if you wish. Namely, the operator which evolves you from here to here is 1, which means you choose the previous green solutions, plus this upper one, which actually allows you to go from the ith to the jth vacuum. So now we get an evolution operator, which as you cross the particular phases where there are kinks, to this operator t that I had introduced before. But now it's easy to do the rest of it. Namely, all we have to do now is to remember that we can have to go all around the circle, and at particular phases around the circle, we get these kinks. So each time you get a kink, you get the corresponding operator, but now we are doing operator formulation of quantum mechanics. We have to time order. There's a time ordering, but that time ordering is the phase ordering of W. The phase of W is correlated with time. So that's the explanation of why we were doing this time order. It's the usual, phase ordering is the usual time order of the quantum mechanics. You time order these operators, you take the product, and that's the result of the path integral. And that's computing for us the index. So now we compute this in two different limits. If you take rho to be very large, we have already said that's how you get this trace of this matrix M. On the other hand, if you take rho to go to 0, you can basically W degenerates to W naught, the critical quasi-homogeneous one, and you have now in front of W an e to the it. But you can rescale e to the it by rescaling the variables now by the corresponding operator that we had before, so twisting the field as you go around, and that's just a twisted with an index. So the twisted with an index in that case computes the UV limit, but since the computation should not depend on the limit, it's just computing the degree of the map, you're relating one computation in one limit to the other one. So there's the relation between the R charges, these degrees, to the kinks. So this is basically the 2D story of the wall crossing. So it involved some kind of a simple idea of using a novel kind of quantum mechanics twisted in some way which we usually don't do in order to show this relation. Originally, back in the 90s, we had proven this statement after a laborious, very long argument using what's called the TT star geometry. So TT star equations helped us to actually prove these statements originally. So the proof I just sketched here was the proof we found in the past year, which simplified the original proof. So it's in line with the development which has to do with this 4D case, the 4D wall crossing, which is more interesting, in fact. That arises in the context of n equal to supersymmetric theories in 4 dimension. And in that case, the analog of the kinks are replaced by monopoles and dions. And monopoles and dions are labeled by elements of a lattice, a charged lattice. And their mass is fixed in terms of the elements, in terms of these lattice elements that they are at. So there's what we call the central charge, Z, which is a map from the lattice elements to complex number. And the absolute value of Z for each particular element of the lattice plays the role of, gives you the role of the change in W's that we had before, and the masses of each particular BPS monopole or dion is simply given by the absolute value of the Z. Now, monopoles and dions can sometimes decay, and in fact, they do decay, as was discovered by Seiberg and Witten. It had to decay for the consistency of the theory. And this again happens for the general argument I told you. The only way that can happen is if the corresponding Z's align. So again, you have a complex number playing the role of the W, and when these lines, when they align, you can have the decay of these monopoles and dions. So originally, in the work of Seiberg and Witten, they basically were forced to have a very specific spectrum for the theory to be consistent. So they had basically consistency condition for the existence of quantum field theory and its deformation told them that there had to be a decay, and moreover, exactly how. Nevertheless, it was a very complicated decay. It involved infinitely many BPS particles disappearing to only 2 particles and so forth. So there's a very novel kind of situation where you could get rid of not only just a finite number of particles that I was talking about here, but infinitely many at once as you cross the wall. Now, there was no systematics to this crossing the wall in the 4D case, and the few cases that physicists worked out were basically based on consistency arguments along the line of Seiberg and Witten. There was no general formula like the ones I gave you for the 2D story involving Picard-Lefschetz theory. There was no generic story until Kontsevich and Soibelman proposed the wall crossing formula, which told you how, they suggested how these numbers, the BPS dions and monopoles, should change. And in fact, also a particular refinement of it by the work of Dimofsky, Gukov, and Soibelman is the one I'm going to be focused on, which involves the following objects. So first of all, there's this electromagnetic pairing, which is a skew-symmetric pairing in the lattice. So the electron and the monopole will have inner product 1, and the monopole electron will have -1, and so forth. In some bases, it's just the usual symplectic pairing. And you can consider a quantum torus algebra based on this, namely take elements gamma in the lattice and define the operator quantum torus algebra given by the fact that if you take the product of them, if you reverse the order, you get a multiplication by a phase, which is denoted by some new parameter, this Q parameter, to the power of this integer, which is this inner product between the gamma and gamma prime. Now, for each dion, introduce the operator, which depends on the charge, gamma, and the spin. It's an infinite product from 1 to infinity of an object which is basically what we call the quantum dialog, a version of a quantum dialog. We have 1 minus q to the n plus s. This s denotes the spin of the corresponding dion. And this u of gamma is the corresponding element of the quantum torus algebra. And so what Kontsevich and Soibelman proposed was that if you do basically the same thing I told you in 2D, but now in this context, if you go around the phase of the z in an order, and if you take a product of these operators, now these operators, each one of them is an infinite product of these q's, I mind you, and these are made of these quantum torus algebra mixed in somewhere in the middle of those. So these u's don't commute with each other due to these guys. So if you take this product ordered according to the phases of the z's, this object is invariant if you change the data of the theory. And based on this data, they propose that you should be able to see the jumping of this BPS dions and monopoles. A remarkable statement. Now, the similarities to what we already talked in 2D is strikingly obvious. Namely, we had the complex phase, a complex plane playing the role of the masses, the difference in some particular points. We also have the notion that there's, for each BPS particle, you associate an operator, and you ordered the operator. The operator looked a little different. You had a 1 plus something, which depended on the corresponding kink. The something here was very simple in the 2D case. Here you get an infinite product of those things. If you weren't there, it would be just 1, but now you have an infinitely complicated looking story. But then you took but nevertheless, the rest of the story is identical once you do this dictionary. As you go around the circle, you compute it, you get an invariant of this data. It turns out that this is not an accident, and in fact, the 4D case can be related to the twisted supersymmetric quantum mechanics I told you about. It's just an infinitely more complicated version of the one I just told you. Namely, you replace the 4-dimensional space by a new manifold. Instead of R4, you replace it by M4, which is a simple geometry involving S1 times an extra space, which is a 3-dimensional manifold, which we call Melvin cigar, which is basically a product of an infinite cigar times R modded out by a quotient, whereas you shift the R, the Z-axis, by shifting R and rotating the cigar with some phase, Q. So you take this 3-dimensional geometry, which is parameterized by Q, times S1. So you basically go from 4-dimension, reduce the theory to 1 dimension. So now you have actually a theory which is n equal to 2, analog, because you have to topologically twist the theory. You get rid of half the supersymmetry. You end up with 2 units of supersymmetry on S1. And now you do exactly what I told you in terms of supersymmetric quantum mechanics on S1. And you can actually show that there's a new additional ingredient in the 2D story that we now have, namely, unlike the examples I told you, it turns out when you get alignments in this particular case, you get infinite many alignments at the same time. That's the new situation that we didn't have before in the 2D story. But once you take into account these new ingredients, you can actually write down the corresponding operator, and it's not too difficult, actually, to show that the operator they wrote down arises as the corresponding object, which contributes. And therefore, the rest of the proof is identical to the 2D case. So basically, 4D reduces to the 1D supersymmetric quantum mechanics, and the results of Consider-Stoyman follows. But now, just as in the 2D, you ask the following question. In the 2D case, the trace of this, the eigenvalues of this monodromy, had some information invariantly about the polynomial, the weight of the causal homogeneous polynomial, for instance. What about now? So here we start with an n equal to 2 conformal field theory in the ultraviolet, and then we deform it to a theory which has these masses, monopoles, dions, and so forth. And it turns out, from what we have just said, it follows that whatever you compute in terms of the monopole and dion data should not depend on how you deform the way. In other words, it's an invariance of the conformal field theory itself. So somehow we are basically computing an invariant of the 4D conformal field theory. So you can compute that, and you can take, for example, a trace of M to some K again, and you compute these objects, but now they depend on Q, because remember we have this other Q in the story, which is part of the 4D geometry. So you compute them, and out of nowhere, you end up getting modular forms. So there is no deep explanation of why we are getting modular forms, but we do get modular forms. And in fact, we get interesting modular forms, and they get related to various interesting identities of quantum dialogues, depending on how one computes these, as well as certain identities of Rogers and Ramanujan. So it's a very rich story. Out of the blue, we are getting something which looks like things we have seen before in the context of 2D conformal field theories and all that. So out of studying this 4-dimensional n equal to 2 gauge theory, the conformal theory of it, no matter how you deform, you're getting some data of a modular form as if you're doing a 2-dimensional conformal field theory. We don't have a deep understanding of why. So for example, the simplest example of this is the 4-dimensional case with n equal to 2 conformal field theory. Perhaps the simplest conformal field theory in 2 dimension with n equal to 2 is the Argyris-Douglas theory. In that case, if you deform the theory away from the conformal point, you get the monopole and basically an electron and a monopole. And if you compute the corresponding trace of the monodromy, you end up computing the trace of this infinite product here. And if you plug it into here, it's not obvious what you should be getting. You have to remember that U and V don't commute. It's a quantum torus algebra. You end up getting this Rogers-Ramanujan function, G, divided by Dedekind eta function squared. And this is also related to the characters of 2,5 non-unitary minimal models. So
Should that be UV equals Q?
yes, thank you very much. Thank you. I'm glad that some people are still paying attention. So UV equals to Q times VU, sorry. And so this gives you the amazing fact that you're getting these objects. Now, these are the kind of things that people have seen in different contexts, like interval deformations of conformal field theories. In some sense, this is, for example, here McCoy and others have looked at these kind of things, very natural objects that arise. Nobody has written this. Nobody has written the characters in this form, so this is bizarre in that form. So it's a new way if you wish to write the characters. And it turns out that if you insert other U's and V operators here, you get the different characters of the minimum model. So you get all of them, not just the vacuum one. You get all the characters depending on what you insert there. So there's a deep relation here which really begs to be understood. We just scratched the surface of it clearly. And just by studying some simple index theory related to a conformal theory, so we have this map from 4D conformal field theories to 2D conformal field theories in a way we don't understand, and it begs to be understood. So I reviewed some aspects of a topic covered in the 2 recent workshops here, and we look forward to many such workshops in the future here at the Simon Center. Thank you.
Thank you, Cumrun.
Morally, yes. That's the W is the same as what we call this the central charge of the mass of the electron and monopole data, right? So there is the analog, yes. That's what I call Z in my talk. Yes. Well, holomorphic. It's not a function. So the 4D gauge theory is not given by a function W of x's. What I meant as an analog is the values of W. So you remember that there's critical values. So the value of W, that has an analog, but not a function W of x.
So in this 2D case, is it correct to say the thing you're computing is sort of the Alexander polynomial of that singularity?
Alexander polynomial, I didn't think about it like that. Is that related to the?
Especially the monodromy of the Milner quadrant.
Oh, then it's the same, yes. Yes.
And is that why you see that? I mean, is that the meaning of that Yang-Baxter relation?
Yes. Then it's related to that.
Other questions? If not, let's thank Cumrun again. And let's thank all the speakers for a wonderful conference. And congratulations to the audience, you survived.